It's a real pleasure to be here. It's a pleasure to see some old friends and some new friends I trust also. And I'm going to take this opportunity to talk about microelectronics in the more than more age. We've gotten used to saying more than more or more, depending on what aspect of the industry you're talking about. But I want to talk about becoming a truly pervasive technology today. So what I'm going to try to do is kind of go back and, as Yogesh said, kind of give you a kind of my perspective, at least, on where this whole business has developed and why WIMS is such an important part of that development and why you're here at Michigan to learn more about it. And we hope that will kind of put things a little bit in perspective for the talks that you'll hear this afternoon. It's kind of interesting to look at the last couple hundred years. About every 50 years, we've seen a new thrust. It was textiles in the late 1700s, steam power, railroads, automobiles, electronics, and now we're talking really about new things, nanotechnology and extensions, microsystems. But every 50 years or so, there's kind of been a new technology that has changed the way we live. The progress in microelectronics certainly has been greater than in any other field of endeavor over the last 50 years, and we all see that, and the pace of technology developments continues to accelerate. So now we talk about nanotechnology and biotechnology and microsystems, and the question is, where did this all come from? Why is it the way it is, and where is it going? I was very fortunate to start my career, I think. I've always felt grateful for the fact that I could start my career at Bell Labs at Murray Hill. It was a big institution, a national resource, looked a little like a prison, but it had experts in almost any field that you could name. This is what it looked like when I started in 1963. And we were working on magnetic memory systems. Probably no one here remembers what those were like, but they were shooting wires through cores. They had little toroids, and they would make memory mats that way. We were trying to break a penny a bit, and Bell Labs was still basking in the glow of the first commercial communication satellite, Telstar, that they had launched the year before. Since that time, microelectronics has certainly been a miracle. To me, I have never lost my fascination with the progress that we have made. It's changed the way we live. The ability to store and process and communicate information has increased billions-fold. Cost has dropped by $1 billion or so. Today, data acquisition and data interpretation can be done at blazing speed. Communication has been revolutionized, and even the ability to sense. Not quite anything today, but anywhere, almost any time. And it's that combination of things that I'm really going to talk about today, and of course, that's the combination that is WIMS. And it's a big business today. This is the top 10 semiconductor suppliers. You can kind of look at the list, but today it's about a $350 billion industry, and that's pretty impressive to somebody that kind of saw the beginnings of it more than 50 years ago now. So if we look at that industry, you know, science really built the foundation. Early work to try to understand semiconductors and semiconductor technology. Research provided the materials. Silicon certainly, but gallium arsenide, gallium nitride, all the dopants for silicon, all the metals that we see used to string things around. Research provided the materials, and technology provided the tools. But the thing that really made it go was manufacturing. That you could take all those things and put them together and make them reliable and make them cheap. That's what did it. And that's what continues to amaze me today. that you can put the complexity that we put on these chips, and it works. And it works time and time again, almost unlimited. So microelectronics really resulted from a partnership between research and manufacturing. The miracle worker was, of course, the planar process. And many people worked on the development of the planar process, but Bob Noyce was the one that really put the capper on it. We have ridden the wave of the planar process now for over 50 years. Bob was the son of an Iowa preacher, and he was a very good friend of my thesis advisor. And I always wondered why Bob Noyce knew me and why I could get in to talk to him. And he came here once, and I gave him a tour around our meager facilities in those early days. And it turned out he was a good friend of my thesis advisor, and I interacted with him on a number of occasions. But Bob was always one of my heroes. I think all of us, as we go through our careers, need people we can look at and say, wow, he was really special, or he returned my calls, or something. And Bob was one of those. He was really an incredible person. But we started kind of humbly, should I say. This chip looks worse than any chip we ever fabricated here at Michigan, I think. At least the ones I saw. My students may not have shown me some, but this was the first integrated circuit, Fairchild 1961, and using, of course, the planar process. But by the end of the 60s, we had seen chips that, aside from feature size, look an awful lot like chips today. This TTL logic gate, nobody in the room knows what TTL was, but stood for transistor logic, I think. In the early 70s, we started semiconductor memory with the 1103 DRAM. It was the first chip probably to make people realize that you could do more than small cache memories with the technology, that it was going to rival magnetic core. And then in 76, we had the 4K and the race was on. I still remember very well, as a young faculty member here at Michigan, one of my faculty colleagues came in and he said, well, I just got back from the Reliability Physics Symposium, and they've decided that they can't make the 16K. Industry's going to roll back to 4K, and that's it. Because we were fighting things like soft errors in those days. And if you don't know what soft errors, you can look them up. But nobody understood what in the heck was going on. Occasionally, memories would just drop a bit, and then they'd be fine. Then another cell would drop another bit. And of course, it was radiation-induced damage, and nobody knew about radiation in those days. So the guys that made image sensors spoke up. But one of the dumbest things I ever did as a young faculty member, my first consulting job, was to get involved with some people that did technology forecasting. And they said, we want you to forecast the future of the microelectronics industry from now until the year 2000. And that was about 25 years in the future. And, I was young and unabashed. And so I sat down and I whipped up a whole bunch of things. We turned it into the FAA, and then Wiley published the thing. And it was published in Japan. And I thought, I'm never going to live this down. The only good thing was nobody bought the book. But a couple years ago, I decided I'm going to go back and I'm going to see how bad it was. How short-sighted can you get? So these are the curves from that. This was DRAM bits per chip. And if you plot the actual numbers, we kind of knew, I'm pretty conservative, that it was probably conservative, but it wasn't horrible. In 2013, of course, we could go out and we could buy 8 gigabit chips, stacked chips with silicon vias to interconnect them, vertical integration, so-called, but it wasn't as bad as I thought. And then I looked at cost per chip. Now, you have to remember that by 1985, everybody in the industry thought we were going to have to go with E-beam lithography or X-ray lithography because you couldn't do it with optical lithography. We were running into wavelength limits. Well, this was Uh, and I can only claim compensating errors must have been present in that forecast. But in 2013, we were 1 million times below a penny a bit. No one in the early days would have forecast that. And today, flash memory, probably about 10 nanocents a bit. That's 100 million times improvement in cost. And we all see that. We walk around with memory sticks in our pockets, and they're non-volatile. And you know, if you look back to the early core days, it's really amazing. Today, lower power, non-volatile flash memories are on the horizon. Things that for microsystem applications you can just turn off, so there's no sleep power, and you can write them at low voltage. And those are going to be enabling for a lot of microsystem applications. So we've seen a lot of progress since the original 4004 microprocessors was announced in 1971. We've seen Moore's Law, which seems to go on, and it has driven tremendous changes in so many things that we do, but it is slowing down. Today, wafer fabs are in the billions of dollars, more than the GNP of a lot of countries, and so only a very few places are going to be continuing to drive the more. That is more scaling, more density, more on a chip kinds of things. So we've already seen vertical integration taking off. So what is there after more than more? I couldn't resist putting this in. Gordon Moore is the only billionaire I think I've ever had dinner with. I doubt if he would know who I am, but these guys are kind of also heroes. Jim Mindo on the left, John Linville, who was my master's advisor, and Gordon Moore. So what about it? Well, of course, the answer to that is WIMS, and the rest of the talk's going to look at why that's so important. In 1980, Fred Busey gave the keynote at the ISSCC conference in Philadelphia, still, I think, in those days, and pointed out that the remaining barrier was being able to utilize electronics by people that were not necessarily skilled in the art, and to get into some additional application areas. And microelectronics has become pervasive in communications and data processing, but its impact on things like healthcare has been pretty muted. I would claim that becoming a pervasive technology is requiring a new electronics, and it's the convergence of low-power microelectronics with wireless connectivity and with sensing that is going to constitute a new electronics. And with that new electronics, we're going to be able to address most of the global challenges for this century. We've already had tremendous impacts in communication and transportation and access to information, but healthcare, the environment, sustainable energy, security, all kinds of other things are now going to fall within our purview. And so if we look at the things coming, this has been called the technology swarm at the edge of the cloud. Well, we all talk about clouds now. I don't think it's up in the air anywhere really, but a lot of these devices, a lot of these technologies are going to be applied to complement VLSI and to help make it truly pervasive. And in a sense, that's really what the WIMS Center is all about. So to go with microelectronics, we need wireless, which is antennas and extension of microelectronics, and we need sensors and actuators and what came to be known as MEMS. And so I want to talk about that and talk about that as the kind of the third essential leg in creating this new electronics. Integrated sensors are really almost as old as microelectronics itself. Generally based on the planar process, adding technologies to that to create three-dimensional microstructures. It was interesting because the MEMS field branched off from microelectronics, and now with microsystems, they're coming back together. This is the technology that is key to data acquisition from the non-electronic world, and that's WIMS. And so in that sense, WIMS is really has created the Internet of Things. If you look at our original proposal, we didn't call it the Internet of Things, but that's what it was. It was the ability to go out and put all kinds of environmental parameters and other parameters on the web. And it evolved from being just kind of cute to being commercial because it was manufacturable. Things like this deep reactive ion etched leaf spring. And Kurt Peterson always liked to present this, and I got this one from Lucas Nova Sensor. But things that 10 years earlier we would have said were impossible to do in silicon are now commonplace. Well, all of the business with MEMS and really microsystems started in 1966. That's the year Fantastic Voyage came out. I never went to see it, but I guess there were submarines that were shrunk and were swimming around in arteries trying to fix things. We haven't quite gotten there yet, but the idea was there. And so really the first project that I saw that I thought was pretty neat that involved sensors was a reading aid for the blind at Stanford. John Linville had a blind daughter. She'd been blind since birth. And this was when the integrated circuits were really in their infancy. He created a direct translation reading aid for the blind. Candy went all through Stanford using this device. All it did was image the black and white printed page and turn the letters into a vibrating array of bimorphs, so you could feel the shape of the letters. And she could read at phenomenal speeds with this thing. But it was a systems project that had a definite goal, and it involved some of the very earliest work on silicon image sensors. And it has always been kind of a miracle to me that silicon was almost ideally tuned to look at our visible spectrum of light. Ideal match to the human eye, and we all know what's happened to these devices over the last few years. In 1982, Hitachi was showing slides like this that they'd made using image sensors, and now we all have video cameras and stuff that we carry around, and they're all on our cell phones, and everybody takes pictures of everything. It's had dramatic effects on things like security, probably also Big Brother watching, but it's here, and it's technology, and it's low cost. So these may have been some of the very early sensors that were evolved, but the processes were for the most part, they were processes that were really integrated circuit processes. But of course, today, if you go to a movie theater, you're probably looking at an image created by vibrating mirrors from TI, the DLP systems, where the image is really reflected on the screen using millions of dynamically varying mirrors to capture color and to capture the image that you want to show. And if you don't like visible light, of course, back in the early 90s, Honeywell developed the infrared imaging technology based on thermal sensing. And those are quite spectacular also in their progress. So the MEMS part of this, the part that involved three-dimensional structures, this was one of those, but it started much earlier. And I'm going to give you three examples from the early days to kind of the present that hopefully will put a lot of the things that we do here in the area of WIMS and the things that you'll see in the talks this afternoon into perspective. All this business of etching silicon and creating little microstructures really started at Bell Labs. It was back in the early 60s. And Bell Labs in those days, junctions leaked. Nobody knew why they leaked. They didn't really know about surface leakage and some of those things. And Bell Labs innovated. They had a very extensive thick film technology in those days or thin film technology they were using for resistors and capacitors. And so what they did was they said, well, we'll put air in between the transistor junctions, we'll isolate them with air. So they called them air-isolated integrated circuits, and it was beam lead technology. And they'd etch these little islands of silicon and then hold them together with these electroplated gold beams. Well, I was on leave from Bell Labs at that point looking for a thesis project, and the School of Electrical Engineering at Stanford was looking for joint projects with the medical school. And someone suggested that we might use beam lead technology to try to record the activity of single neurons in vivo at many points at once. In other words, try to get a handle on how the body, how the nervous system processes information, both for prosthetic devices and for what we'd now, in this day and age, call biomimetic devices. And so I guess a thesis was born, and that thesis continued and got me a degree. It was some of the early work in applying this silicon etching technology to sensing structures. But it was as hard to make the second one as it was to make the first. In other words, the technology was really not in place yet to do what you wanted to do. Nevertheless, the technology was used. Within a couple years, they were using it experimentally to probe the visual cortex. People were interested in making a visual prosthesis for the blind. And so I, terrified though I was, went on a couple human surgeries in Philadelphia where they were trying to figure out if you get hit over the back of the head, people say you see stars. Well, so what they wanted to do was stimulate electrically the visual cortex, which is back at the back of the head, and try to understand how far apart you could stimulate and still get two distinct points of light in visual space. They were thinking of building a TV camera that used an array of electrodes and could create images back there. About 4 or 5 years ago, I was sitting in my office and my secretary came in and she said, "We got to throw out all these magazines." And I looked and she had these stacks of electronics magazines. Few people may remember electronics here either. But I looked at it and said, "Oh, that's the whole history of the development of microelectronics. We can't throw these out." And as a result, you should see my basement. I whipped one open and I looked at it, and here was this image. Now I worked with the guys at Utah a couple years before this, but this was from Electronics, December 20th, 1973. A blind patient is sitting here. Supposedly, they're inferring that he's drawing patterns that are being generated on this DEC Graphics 40 system. And so that he, the points of light, he's getting that and he's drawing it. That may have been just a little optimistic. We could kind of do some of this 40 years later, but not at the time. In fact, a lot of times you didn't get points of light, you got auras and things. We weren't quite ready. So it took a long time to develop some of this technology. But today, we can make dense electrode arrays that are capable of instrumenting virtually every neuron in a volume of tissue. Systems are coming, cortical microsystems that are wireless, that have processors built into them to capture the data, to analyze the data, to put out only the most important features of the data. And today, this area is a hot area. It's way above critical mass. Michigan was probably the principal pioneer in this technology. I think something between probably 200 to 300 million is being invested in this area today to make better tools for understanding the brain, both from the standpoint of neuroscience, understanding how it processes information and The links there are to biomimetic devices, but also prosthetic devices for blindness and deafness and epilepsy and Parkinson's disease and so forth. I'll make mention of that a little bit later. But Michigan continues to lead in this area. In fact, one slide that I'll show that Professor Yoon may show later, which I think is just terrific, is the ability to build LEDs on some of these probes at the 10 micron level to stimulate the electrons optically, in addition to stimulating them electrically, recording their activity electrically. And in addition, this puts us in the position where we can do electrical recording, we can do electrical, optical, and chemical stimulation, and chemical sensing and optical sensing, all on these very, very tiny probes that have shanks that are down in the 20 micron wide range. And so this is technology that I think is going to spark a revolution in neuroscience, and will lay the groundwork for some prosthetic devices to treat our most difficult disorders. In fact, we're partway there. Over 250,000 cochlear prostheses have now been implanted. Michigan is a center for implanting those kinds of devices. Many people that are profoundly deaf can talk on the telephone and lead relatively normal lives today using this technology. Deep brain stimulation is now the preferred treatment for Parkinson's, severe Parkinson's. Over 100,000 of these devices have been implanted. The first visual implants for the brain finally have been approved by FDA. And that's after 40 years or so since the early efforts. They can be effective mobility aids. I don't think you're going to sit and read the New York Times with these devices, but they're going to give people mobility to move around on their own. And work is underway on prostheses for epilepsy and paralysis and other disorders as well. So the whole area of electrodes and interfacing with neural structures is now way above critical mass. But in the early days, the technology for those little probes was seen by people at NASA, and they said, maybe we can create catheter tip pressure sensors that will allow us to do the same thing. They'd been using stretched metal foil devices. And so we did that, and these were the first devices, I think, of their kind with built-in micro machine rims. And they were done by a very good friend of mine, Samaun Samatakun, who was an Indonesian student at the time, and later in his career was the head of the Indonesian NSF. We also did some strain gauges and stuff and worked with people over at the medical school at Stanford. And after having glued leads on these structures for a while, I decided that it wasn't something I really wanted to do for a career. And it emphasized the fact that implants are really all about leads and interconnect. And the fewer the better. So I got to Stanford, or to Michigan, and I said, why don't we build this? This is beautiful. Okay, so it's a capacitive device. And the way it works is there's a little circuit in there, uses that capacitor and slowly charges it up. It's powered by a galvanic cell on the back of it. And when it gets to a certain threshold, of course, it fires and it dumps a current through a little loop antenna on the thing. Today we would probably call that ultra-wideband. And it sends out a frequency, and that frequency represents the pressure. Darn, that was fine. We never built it, of course. We didn't have the technology to build it. I didn't know how to build it. But it had a lot of interesting elements. 30 years later, we were building cardiovascular stents here that could go into the carotid arteries and could be powered wirelessly from the outside, and which would operate using backscatter telemetry and allow us to measure any restenosis occurring across a stent implanted in the artery. This technology is going to get better and better. Eventually, we'll make it to the coronaries of the heart. We're not there yet. But we're getting close. This is an intraocular pressure sensor that was shown at this meeting, at these meetings a few years ago. This is a device that wakes up, takes data, intraocular pressure, and you need that for treating glaucoma, and goes back to sleep. And then it wakes up a little later and takes another data point, and it stores all this. So it includes a pressure sensor, a rechargeable battery, a wireless link, an embedded processor, all in a little glass package. 1 cubic millimeter. The sleep power is about 30 picowatts. And you've seen this technology that Dennis Sylvester has presented in these meetings. He'll speak again this afternoon. But the device itself is kind of an interesting little capsule. Again, 1 cubic millimeter. But with all these things in it, and when you sit back and you talk about trying to break a penny bit, this is really amazing that you can do all that. And in fact, you can. It's stacked. It's a different technology that was developed here at Michigan. But it's a device that I think represents the convergence of, again, sensing, very low power electronics, and wireless connectivity, all in one little thing. And finally, the last of the examples, the early work on catheter pressure sensors at Stanford led NASA to select making a single-wafer gas chromatography system. Now, you've all seen a lot of chromatography if you've been at these reviews in the past. And I wonder where that came from. This was the project I most hated to leave when I left Stanford and finally made my way to Michigan. The idea was, why can't we put an injection system, a separation column, a detector, and integrate all of this on a wafer? And in those days, wafers were 2 inches in diameter. And if you could do that, in fact, this was targeted at the Viking Mars mission in 1975. We didn't get there, but it planted seeds that I think were very important. This is the wafer. You might wonder why the top and bottom are cut off. Well, we couldn't get a 2-inch wafer in our 2-inch furnace tubes, so you didn't have any choice. You had to cut them off. This was a Strontium, Barium, Niobate Pyroelectric detector. And you have to remember that this was all done before microprocessors. It was done before much in the way of sensor technology. Probably was the first integration of fluidics using silicon and micromachining. In 2012, we demonstrated a palm-sized gas analyzer. This was really all designed and put together by Robert Gordenker, who's here. I think we ought to put it in our historical artifacts collection, Robert, because it's pretty cool. The fluidics, of course, it wasn't very well integrated or very completely integrated. There's a power level here and communications, and the fluidics is all really right up here on the top board. So it could be shrunk an awful lot. But the fluidics used very, very low mass separation columns that would plug into the other chips, ultra low mass fluidic capillaries, and you could put these things together. This is a shuffle MP3 player, but the size of that white circle there is about the size of a quarter. So these are small enough to go in a cell phone. And it's pretty interesting that you can still get reasonable separations out of things like this. And Ted Zellers will talk about the current status of the GC efforts this afternoon. But I think all of the areas that we started with and many, many more have made tremendous progress. You'll see this later after my talk, Khalil Najafi is going to talk about his work on inertial devices, state-of-the-art work. I think the WIMS effort here, the work at Michigan, really leads this area of combining sensing with low-power electronics and wireless. And I would forecast that these technologies are going to be places that we can't yet dream. It's going to be an interesting time. So I've seen a number of paradigm shifts in my career. I got my first transistor radio back in the late 50s. I was probably late with that, but transistors really created what we know as microelectronics, integrated circuits, and now integrated microsystems. And I think microsystems that can run forever, can sense, can interpret, communicate wirelessly, that's defining what I would call a new electronics, and that electronics is going to be pervasive. So I'm going to conclude at this point. The scale and paradigm is really shifting. Many companies have gone fabless. I think we will continue to benefit from improvements there, but if you're into areas that demand low power in particular, it may not be that you want to go much smaller in feature sizes. We still run for a lot of the things that we do 0.18, and I think that's not a bad compromise between leakage and density. Microsystems are going to be generic at the component level, application specific at the system level. We need more effort on standards. There are still weak points in the component arsenal, in materials and in processes. But the applications of this technology in security and healthcare and infrastructure monitoring and transportation and energy, education, food production, and the environment are really going to be profound. So I would just conclude by suggesting that this new electronics is going to be pervasive in the sense that perhaps Fred Busey was thinking of. They're going to be key to solving the problems of the 21st century, and they're going to be exciting. And so I don't know if I came in too early or too late in my career. You know, I remember back in I won't tell you the date, but when I got my PhD, we sat around grousing about the fact that we were getting out too late. Everything had been done. And you could buy phase lock loops on a chip and op amps, and there wasn't anything else left. I guess that was a little short-sighted, perhaps. But I like this quote from Albert Einstein. He said, "Scientists investigate that which already is. Engineers create that which has never been." And I'm really glad I got to spend my career as an engineer and as a teacher. I don't think I could have asked for anything better than that. So that's what WIMS is really all about, and we, again, appreciate all of you being here today and being able to share kind of the latest in the research results in all of these areas. But this is kind of background for kind of where we are and why we are and why we think it's exciting. So thank you very much.